right, I am going to define quotient maps, quotient topologies, some of the intuition behind it, and an application, just a homework problem you'd see in a textbook. So let's start with the intuition behind what a quotient topology is. So say we have a shape, a square, and let's define these sides with equivalence classes A and B. Basically, all this is saying is if we have a point A, let's say on the same height of the square, with the equivalence class, these 2 points are the same point. We can map them to the same point. We'll do that with a surjective map. But anyways, using that, we can paste these sides together. So say we start with sides B. Well, we'll simply just get a cylinder. This should be like that real quick. But yeah, we'll get a cylinder, and see we still have our side A here. But we've pasted those sides together, and now these sides really are an equivalent point for each point on either side. And now we can do the same thing with sides A. If we paste them together, they'll wrap around and we'll get a torus. And we still have where that side A would have been, it's right here. And we still have B. And why this is useful, say on this shape, we have a topology defined on it. What we can do is we could take that topology and a mapping using those equivalence classes, and we can form a topology on this shape, the one we care about. And it will help us when we know a lot about this space or this shape, but not necessarily as much about this shape. And so let's get to the definition of a quotient map. So the definition of a quotient map we'll define it as let X and Y be topological spaces. Okay. Let P be a surjective map from X to Y. We call P a quotient map if and only if for U subset of Y, U is open in Y, if and only if P inverse of U is open in X. All right, and this should sound really similar to the definition of continuity, or of a continuous mapping. If you look at it, so we have our space X, our space Y, both topological spaces. We have some mapping P. Well, this is saying if we have an open set U, P inverse of U, P inverse of U is open. But it's also saying if P inverse of U, where U is some subset of Y, is open in X, then U is open in Y. However, the definition of continuity, if we have some continuous function f, what it's saying is if we have an open set V in Y, f inverse of V is open in X. However, the difference is if we have f inverse of V is open in X, we don't necessarily know that V is open in Y. And so that's the fundamental difference. This is why in some textbooks you'll see that they call this strong continuity. Okay, so let's move on to our application. So we have this problem. Let P be a map from X to Y, a continuous map. Show that there's a continuous map F that takes you from Y to X, such that the composition P of F is an identity map for Y, then P is a quotient map. So remember, there's 2 criteria to prove that a function, a map, is a quotient map. So number one, we have to prove it's a surjective map, and we can do this using the given fact that it's an identity map, and that simply just means that P of f of y equals y for all y elements of our space y. And writing that out slightly differently, we can see for all y elements of y, there exists an f of y element of x, such that P of f of y, this element of x, equals y. And this shows us that for every y element of y, there exists an element of x such that P of that element equals y. And so there we have surjectivity. Now to prove that our quotient map, that for any subset V of y, V is open if and only if P inverse of V is open. To prove that, we use this function f. So let's start with a subset V of y, and suppose that P inverse of V is open. We're going the first, it's an if and only if statement. We're proving the first of the two criteria. So by definition of continuous map, since P inverse V is open, then F inverse of P inverse of V is open. Just like I was showing you at the very beginning of this video, the definition of a continuous map. And so if we have that F inverse of P inverse of V is open, well, F inverse of P inverse of V simply just equals V, since we know it's an identity map. Thus, V is open. That's our first, going the first way. Going the other way, we have to show that for V subset of y that is open, then P inverse V must be open. Well, it's a continuous map. P is a continuous map. So I can just say let V be a open subset in y. By definition of continuous, P inverse is open in X. And there you have it. We prove that P is a quotient map. I hope from this video you're getting some intuition on what quotient maps and quotient topologies are, some insight on the definitions of quotient maps and quotient topologies, and learn a little bit from this example.